one member of our team, and we will talk about a few news related to space that happened recently. After that, we're gonna have the presentation by tonight's speaker, and during that presentation, you can ask all the questions you want on YouTube, Facebook, Twitter, all the social media, and I will ask your questions later on. And after that, we can all move to the Zoom pub to have the pub quiz, and then enjoy a nice beer, during which we will have the opportunity to talk with our team and also with the speaker of tonight. And speaking of, then tonight we have the amazing Rebecca Larson, which is a PhD student at the University of Texas, working on observing the galaxies at the beginning of the universe. And fun fact, she's also in the Astronomy on Tap team of Austin. Hello, Rebecca.
Hi, thanks for having me.
It's a pleasure. And joining us for discussing a few news of astrophysics is our own amazing Katja Frantseva, who is part of the social media team. So all these nice calendars you've seen, she has been doing them.
Hey, thank
with
you.
Valentina, that you might see later on. Hey, Katja. So we can already move on to the news of this edition. So questions for the both of you. Do you know which is the first planet on which we managed to get an object?
Like that we landed something on?
Yeah, we've landed something, let's say. We've
crashed or landed, like success, like is it still intact?
No, crashed. Yeah.
Oh.
The first thing
Venus? Was it Venus?
Yes, it was Venus.
It didn't go well, but I think we made it.
Yeah, exactly. So it was the USSR that launched Venera 3 in November 1965, and which flew for 105 days and then crashed on Venus on the 1st of March. That's why it's an interesting news of today, 1966. And so it was a success because it managed to make it to Venus. The problem is it crashed and gave absolutely no scientific data. So
I have to say that I tried to read a little bit about Venera 3, and I found a mention of it in one book that is called New Cosmic Horizons, Space Astronomy from the V2 to the Hubble Space Telescope. And so there was a mention of this mission. And well, it's written by, I think, American author. So he was saying that there has been an information that Venera 3, that communications with Venera 3 had been lost 3 months earlier than stated by Soviet Union. And so he says that, oh yeah, that maybe actually the probe had never crashed on Venus. So I don't know if it's true or not, but I found this fun mentioning in the book.
So you think it would be like a lie and it would be propaganda of saying we managed to do it? Possibly. I mean,
I really don't know, because I mean that was during the times of the Cold War, right?
Yeah.
And so if you have I don't know, if the book that mentions this is not written by I don't know, ex-Soviet scientist, and then it's written, let's say, by the other side of the story, then yeah, I would just say that it's very controversial. So who knows?
Yeah, quite a big. I wasn't aware of that, so that's quite interesting. Yep.
Well, just for whatever it's worth, it's incredibly hard to do these things. And so even like launching it into space successfully is an achievement, and getting it in the direction of Venus. And even if you lose, like, I mean, there's so many things that can go wrong at any given point.
Yeah.
And the communications array on a satellite that's traveling super fast away from the Earth towards another planet that's also orbiting the sun in a different speed and all these other things is incredibly complicated. And so, you know, there's all kinds of things that can go wrong, and whether it's communications or crash landing, you know, it's still an achievement to get as far as like, you know, in 1966, like that's still, I mean, either way, I still think that that's really exciting.
And so, yeah, that's why they say it's a ballistic success, because they managed to get it there. So that was already a big
success. I like it.
But then that gives a perfect transition to this picture that you can see here, which actually is Venus. And this picture has been taken by has been released recently, and actually has been taken by the Parker Solar Probe during its third flyby in July 2020. So Venus flyby. It's already done its fourth flyby just last month. And yeah, this picture is really amazing. It's a real picture taken by the probe on its way to the sun. And just to give you a bit of information on this probe, the idea for this probe has originated in 1958. So it's been quite some time that they wanted to launch it. And its mission is to study the corona of the sun, and not the corona here on Earth, its winds and the structure of its magnetic field. And fun fact is that the 29th of October 2018, it became the closest human-made object to the sun. And so we were speaking about this trajectory and how hard it is, but here they launched it, and then it's gonna go 7 orbits around the sun using Venus to increase in speed. So the computation to get these trajectories and things must be crazy.
Yeah, I think it's very cool. And also the very cool thing about the picture itself. So I think that the camera was actually on the probe is set up to take pictures in the visible, if I remember correct. And so they were very surprised when they received this image, because they were just expecting to see some clouds on Venus, but instead, in the middle of the picture, this dark spot, that's actually the largest highland region of Venusian surface. And so, yeah, they're still surprised that they kind of detected partially the planet in infrared. So I think what they're trying to do now is to test also the camera in the lab and to see how much they're sensitive to infrared, because then it will allow new scientific possibilities for the main scientific goal that was studying the corona of the sun. So I think that the team of the probe is very excited about these new possibilities.
Yeah, I mean, but the picture is really, just to think just a picture of it so close, it's crazy.
Yeah.
And yes, of course, the big news of of last month is the rover that we managed to get on Mars. That landed on the 18th of February 2021. You can still get the video on the internet. And did you guys watched it?
Yeah.
Yes, absolutely. I watched the live like press release when they released the video, and like talked about like everything that you're seeing in it.
Yeah, it's super cool. I really like all this. Now we're making these kind of events, or the black hole picture thing, very like international, and everybody can access it and really understand what's happening. And I found that super cool. Do you know what is the main mission of the rover?
Yeah, well, it's to one, it's of course to look for habitability. So basically to find to study the environments on the Martian surface, and just see if they were capable of supporting microbial life in the past, and also to take samples. So the idea is to collect rock and soil samples, and then store them, and then potentially bring them back to Earth. Because for now, the samples from Mars that we have on Earth, it's from Martian meteorites, which is very cool because we get them for free. So it's like, you don't have to invest a lot of money, and then kind of hits you on the head.
You just wait for it.
Yeah, you just wait and you hope that you'll be so lucky, then the orbits will cross in this amazing event. But yeah, the idea is that still the Martian meteorites that we get on Earth are, and they still had to travel through the, through interplanetary space, and it had to enter the Earth's atmosphere, and so in some way the sample was altered. But if you have a cool rover on Mars and you can take the samples and then protect them and carefully bring them back to Earth, that will give you a whole new set of information that we were just not able to get before. So I think it's really, really cool.
It's amazing. It has tons of instruments. This rover, it's crazy. And
there's a lot of really other cool, like, tiny things that are awesome. Well, none of it's tiny. All of this is a huge, like, again, a big achievement, and all very, very important steps, especially like moving forward into other space exploration. There's a cat. Sorry. I'm not crazy, for anybody on the stream who can't see the other screen. There was a cat in it.
There's a cat.
So there's material on the rover that we're planning and hoping to use in spacesuits for actual human exploration or in habitat creation, trying to test what the elements living on the surface of Mars is going to do to those materials and if they're going to withstand that. And so we know what we need to use to send when we want to build more established presence on the planet itself. And that seems like such a small thing, but it's also incredibly important to enable like future missions going forward, along with, I'm sure, all the other things you're going to talk about.
Yeah, and that's most of the.
Yeah,
it's really to give a taste to people to go check it out. I've seen that also the rover is supposed to test for oxygen production on the planet, like to get human there. So it's already, I find it huge that you're already looking at that, like just, oxygen production. And for people who are interested, you can find a super nice 3D model of the rover on the NASA website, where you can look at each component and really, they can tell you all the instruments that are on it, and it's amazing. It's really, really cool. I really encourage you guys to go check it out.
And there's a helicopter. There's a helicopter.
It's gonna fly
on another planet, you guys.
We've done it. I didn't know I wanted it so bad until it came.
Right? There's just so many really cool things, and there's a lot of information. You can watch a video and you'll see for the first time landing on another planet. It's incredible and it's inspiring, and the people who put these cameras on the rover and on the spacecraft and on the jetpack and on like all of the other things so that we could witness this as a species, I think are doing more for humanity than even just the science that's going to come back from it. I think making it accessible to everyone, like you said, where it's much more of a global endeavor, and it's much more shared publicly and inclusive, I think makes a huge difference, because what we do is important to understand the universe and our place in it, but it's more important to share that with the rest of humanity, because that's why we're doing what we're doing. And so I think making these kinds of videos where people can actually see this happening. There's a microphone. There's two. Well, there's a microphone on this rover. You can hear the sounds of another planet. And now, like, even people who are visually impaired can experience what this was like for us to do. And I think that making those kinds of experiences even more accessible is an incredible endeavor. And it's also scientifically relevant, right? There's all these scientific reasons and benefits to doing these things. We got to actually make sure everything deployed properly and test it and witness it happen because we had video, but we also are going to be able to like use the sound for science purposes as well. So it's just all of the things. This is not what I'm here to talk about.
For everybody who is interested to talk about it more, don't hesitate to join the Zoom pub at the end, because I'm sure we're gonna talk about given how excited we all are about it. Yeah, and as a last fun fact, actually, about this, how we were talking about involving people, is that you could send your name to Mars, because the scientists were engraving on a chip with an electron beam, like the name of like 11 million people. You could just submit your name and get it out there on another planet. I mean, yeah, it sounds silly, but I think it's really cool to give some visibility to these kind of things. Ah, yeah. Let's talk about it.
Okay, pause on that.
So then, very briefly, as the last news, for people who are in the north of Netherlands, you can participate to a very cool thing where I don't get all the detail, but you can go out and count the stars you see, and that will fill in a form, and that will help scientists to get the light pollution and how it works in different area. And so I think that's super, super cool. And I was thinking that for other people in other countries, there might be more initiatives like that. So if you guys want to help science and participate at your own level to scientific projects, don't hesitate to always look for this kind of citizen projects, that there are more and more of these that involve anybody who wants to help to do like any tasks. So I think it's really, really cool. Yep. That was the last thing I wanted to mention. And so now I guess we can move on to the talk. Yeah, ciao, Kaita.
Bye-bye. Good luck, Rebecca.
Thank you very much for joining us, and we hope to see you in a further edition. And Rebecca, you can start your presentation. The floor is yours. Enjoy.
Thanks. Hi, everyone, officially. So I was introduced a little bit earlier, but I also wanted to just say my name is Rebecca Larson. I am a PhD student at the University of Texas at Austin. I'm an NSF fellow, a National Science Foundation fellowship holder, and I also, like they mentioned, host Astronomy on Tap in Austin, or AOT ATX. If you're interested in any of the shows that we have done, I believe we've put the link in the YouTube description of like how you can reach our website and all of our social media and our YouTube and all those other things. We have a lot of talks similar to this, and so if there's something else that maybe you're interested, you can always check that out. So what I will be talking about today is not Mars, although it's very exciting. I'll be talking about what I do specifically in my job, and that's to search for galaxies at the very beginning of the universe, both from Earth and from space. So I personally don't get to go to space, but the telescopes do. So I'm going to talk a little bit about how I do my job. And hopefully that's interesting, because I think it is. So what do I mean by the beginning of the universe? So here I'm showing kind of a schematic of the history of the universe here, or cosmic history. And so what you'll see on the left-hand side is the beginning of the universe, and on the right-hand side will be today time. And so time will be increasing to the right. And what we have at the beginning is the Big Bang, and then the cosmic microwave background, which are all things that are very interesting, but I'm going to skip over. Then we have first stars and first galaxies starting to form. We have something called the Epoch of Reionization, which is predominantly what I study. But again, we're going to kind of skip through some of that. If you have more questions about it, please feel free to ask. And then we have today's universe. And so what we're trying to do is we want to study galaxies through time, and we want to understand how those galaxies from the beginning of the universe, from the beginning of when galaxies started to form, evolved into the ones that we see today and the one that we live in. And so in order to do this, we need to look back in time. Well, conveniently, telescopes are time machines. And so because light travels super, super fast, but it still only travels at a finite speed, this only goes so fast, that there's only so much time that has passed since that light was emitted. And so what ends up happening is if you look at something very, very, very far away, it takes time for that light to travel to you. And so by the time the light reaches you, you're seeing what that object or that galaxy looked like when that light left it, which sometimes can be, you know, a star nearby. The closest star is 4 light years away, meaning it took light 4 years to travel from that closest star to us. And so we aren't seeing that star as it is right this moment. When we look at it, we're seeing what it was like 4 years ago. And so that's nearby in our own galaxy and in our own little local neighborhood. But what I'm studying is I'm studying galaxies from the beginning of the universe. And so the universe itself is about 13.7 billion years old. And we want to study galaxies that happened in the first billion years of the universe's history. And so I'm looking at things that existed 13 billion years ago or more, hopefully more. And so it's taken the light that long to reach us. And so in a measure of how far away an object is when we look at it, astronomers use a term called redshift, which just means that the light emitted shifted to redder wavelengths. And we chose red because red light is at a longer wavelength than blue light. Astronomers shouldn't be allowed to name things, but that's kind of the concept behind it. And so what does that exactly mean? That it's stretched or it's emitted or whatever. So a galaxy will emit, let's say, blue light. So you have a star that emits a lot of blue light. And you can see here at the top, you'll see the little blue wavelength, and then you'll see the galaxy emit it. What's happening is the universe itself is expanding. And so again, this is probably a subject for another talk, but let's just assume that we are looking at a universe where it is expanding, meaning the space itself is getting stretched. And so the light is stretching as it's traveling from that galaxy to us. And so while it was emitted far away enough in the blue, as time progressed and that light traveled towards us, the universe was expanding. And so that light got stretched out. And by the time it reaches us, it gets stretched so far that it's in the infrared, if it's, you know, the galaxies that I'm trying to find. So that means that if I'm looking at a galaxy's ultraviolet emission, where all these big, bright new stars in a young galaxy are being formed, emit a lot of ultraviolet light because they're very, very bright and very, very hot. But it's taken 13 billion years for that light to get to us. It has been stretched so far that is now an infrared wavelength of light. And so you can see on the right, there's a little kind of animation of what it looks like when two different galaxies, maybe the same galaxy type, emit the same kind of light, but at different distances to us. They will show up at different wavelengths. So one will be around the green and one will be around the red. And I'm using these colors as just kind of analogs because there's a whole electromagnetic spectrum. But I just want to show you a little bit about what it looks like when we look for these distant galaxies. So this is a lot to look at, so it'll repeat itself. But what you're seeing at the top is a little schematic of the Hubble wavelengths that it can look at. So if we want to look at light with the Hubble Space Telescope, these are the different options we have to take pictures. And so all the bottom is different pictures taken by the Hubble Space Telescope at different wavelengths of light. When you want a color image, you got to stack those all together. You got to color the purple one purple and color the blue one blue and color the green one green, etc. And then you put them all together to make a color image. That's how we get those really pretty pictures of space. But as scientists, we look at all of those things individually most often. And so what you're looking for is you're looking for these distant galaxies to show up at specific wavelengths and not at others, because this shaded in gray spectrum that is moving across the screen to the right is the light emitted by a galaxy. Galaxies emit light at all kinds of wavelengths. But the problem is the further away they are, not only are they fainter, but all of their light kind of gets eaten up by running into stuff in between us. And so what you're seeing is you're only seeing the part of the galaxy spectrum that is not being absorbed by all of the material in between us and that galaxy as it traveled through the universe. But you're seeing it also be redshifted. So all of this light that was emitted in the purple or the blue was actually showing up when we observe it in the infrared if it's far enough away. And so you'll see that it shows up in some images and not in others. And so this is how we can tell the distance to a galaxy. So when I say I'm looking for distant galaxies, I'm looking for galaxies that look like this in the images that we have from example, the Hubble Space Telescope. And so if a galaxy doesn't show up in all these blue ones and the green and the yellow and only shows up in these two red ones, those are ones that are super far away at a high redshift being early on in the universe. And so again, I'm talking about different wavelengths of light. So this is the electromagnetic spectrum, or just light waves, and galaxies emit them in different wavelengths, like I said. And so what we're showing is this ultraviolet light, which is shorter wavelengths. And then as it goes to the red, there's a little graphic of visible light that shows kind of like blue and purple all the way to red. It's a rainbow. That's how rainbows are made. And so it gets stretched into the red. And so when I'm looking for these distant galaxies, I'm looking for this ultraviolet light, all these big, bright, brand new stars that were formed in early galaxies in the early universe. But I can't look for ultraviolet light from these galaxies because it's been stretched into the infrared, which is fine. I can use a telescope that looks at infrared wavelengths of light, and then I can see those galaxies. I just have to know that what I'm looking for is not infrared emission from the galaxy, it's ultraviolet stretched into the infrared. And so this is great. We can do a lot of things with different telescopes. Some telescopes look at visible wavelengths, some look at gamma rays, some look at radio waves. Shout out to Jackie and to Alma. And then some look at infrared. And so what I want to do is I want to look at infrared wavelengths of light to look for my galaxies that existed over 13 billion years ago, because that's where their light has been stretched into, the specific thing that I'm looking for. Unfortunately, the atmosphere here on Earth kind of blocks a lot of infrared light. Now, I'm not going to say I don't want there to be an atmosphere, because I do enjoy breathing, but it kind of is a problem when I'm trying to do my science. And you'll see here at the bottom, this like shaded orange is about how much of the atmosphere blocks light at different wavelengths. And so you'll be able to see like visible light makes it all the way to the ground. The atmosphere doesn't block it. And there's some argument to be said about that's what we see in. That's why it's visible, is because those are the wavelengths that reach us, and our eyes have adapted to be able to see the things that reach the ground where we live. Infrared is mostly blocked, and radio waves are pretty clear. And so I'm actually going to not talk too much about radio waves. We have a couple talks if you're interested. I can find the links for you about how we study things with radio. But I'm going to focus on infrared. And so you'll see that the infrared portion of the spectrum, that part where there's like a little telescope under the wavelength, is actually absorbed a lot by the atmosphere. So it's harder to do from the ground, but we still do it. So this right here is a really cool graphic that I like to look at because it puts a lot of things into perspective. When you want to use a telescope to go look at galaxies, you need to go collect their light. You need to go take a picture. Basically, you need some source that's emitting light or electromagnetic waves, or however you want to call it. And then you need to take a picture of that. So you need all of those light waves to hit your telescope and then take a picture. And typically, what you need is you need bigger light buckets. You need to collect more light if you want to look at something faint, because it's going to have fewer light waves hitting you. And so a bigger mirror is better because you can collect more light and you can see things that are fainter. Now, fainter might be something nearby that's very faint, but it also is true that the further away something is, the fainter it is. So just like if you had a flashlight and you walked away, it would be fainter the further away that you got. So the same thing happens with light emitted from galaxies that are far away. And so the other component of this is that if I'm looking at longer wavelengths and I want to have a good high resolution, if I want like an HD picture like Hubble takes in the visible wavelengths, for a longer wavelength, I need a bigger telescope, because that's how the resolution is determined. So TLDR, you need a bigger telescope to look at longer wavelengths at a high resolution and to collect enough light to look at fainter things. So I also want to point out here at the very bottom on the left is the tennis court, just for scale, because those are typically standard size. Right above that is the mirror size for the Hubble Space Telescope. It is 2.4 meters. It is very small. And it has done a lot for science, but it's also very small, and it's in space, because getting to space, like we mentioned, is quite difficult. And so getting a bigger thing to space is quite difficult. And it's also going to be a harder achievement to like maintain and keep intact and all those stuff. And so you'll see a lot of these mirror sizes are much, much bigger than Hubble, mostly because they're on the ground. And so I will point out some of my favorites. Kind of towards the top in blue on the right-hand side is the Cac Telescope. This is a twin telescope. It's in Hawaii, and I have been using it for the past few years, so I'll talk about that in a second. But that's the size of that mirror. And I also want to point out the James Webb Space Telescope, which is down in the bottom left next to Hubble, and that's the size of its mirror. And then towards the bottom in the green is the giant Magellan Telescope, which is the next generation of 30-meter class giant telescopes. And so all of these really big ones are typically on the ground because it's easier to build big things on the ground because you don't have to launch them into space, which is complicated. But the James Webb Space Telescope is going to be launched into space, and it's a much bigger mirror than Hubble. Stay tuned why that matters. Okay, so let's talk about how we search for the first galaxies from Earth. Now, this is a very beautiful picture. This is our galaxy that you're seeing here in the sky. This is the Milky Way. And then this is some of the telescopes that we use from the ground to look for distant galaxies. And then off to the right, yes, absolutely, that is a laser, which I don't get to use, so I won't talk about. So the Keck Observatory, like I mentioned, this is it. These are the twin telescopes here. And in fact, what we've done with Keck is really, really amazing. So you are looking for galaxies that are super far away. You're looking for infrared light. So you need something big because you need the resolution, and you need something big because they're very, very faint. So Keck is one of the biggest telescopes that we have right now that's capable of looking in the infrared wavelengths for light. And so in 2013, we broke the record for the most distant galaxy. The galaxy that is the furthest from us means it's the galaxy that was existing earliest in the universe that we've been able to study. So in 2013, my boss, Dr. Steve Finkelstein, actually broke the record by discovering this galaxy, which is so aptly named Z8 GND 5296, because again, we shouldn't be allowed to name things. But this galaxy existed a billion years after the Big Bang. And so it existed 13 billion years ago. And we were able to study it and detect it and see these signatures of light in the infrared that we know were emitted in the ultraviolet. And then the amount that it was stretched tells us how far away this is. And so this is a little picture we have here from Hubble of the field that it was discovered in, and then a little zoom in image of this galaxy. And you'll see that it's quite red because, like I said, the light was stretched out so it shows up in the infrared. And so it's been colored red appropriately in the images so that it appears how it would appear if you were to look at it if you had infrared eyes. And so this is very exciting. We're looking 13 billion years into the past. And also it's very exciting because, you know, my boss did that. But records are meant to be broken. So how do we break this record? How do we go further back? So like I said, the atmosphere is kind of a pain. And so ground-based observatories, and this is a little bit of an outdated plot, and again, unfortunately, I'm not magic at like PowerPoint, so I couldn't invert this for you, because on this plot, on the left-hand side is today, and on the right-hand side, it's the early universe. And so we're looking in the reverse order. So time is increasing now from right to left, and redshift is increasing from left to right, meaning higher redshift is further away, is earlier on in the universe. And so at the bottom there's some analogs to how old redshift 8 or 10 or 1 is. So redshift 1 is 6 billion years ago, meaning it was half the age of the universe now. And then each redshift, you get about half towards the next step. And so what we're looking for in this galaxy that we found was at redshift 8, that's what the Z8 is in the name, creative, existed at, 700 or so million years after the Big Bang. So 13 billion years ago. And so you can see that with the ground-based observatories, we're actually getting further than what this says in this plot, but you need to have the right conditions, and you need to already know kind of where to look and all these other things. And so Hubble, with the instrument capabilities it has, is able to look quite far back in time. And with different instruments that were put on Hubble, there's 3 different pictures that include Hubble with an arrow here. And that's because we were able to go and service it. We were able to add new instruments and to upgrade the telescope after it was already launched into space. And so not only did we launch a giant telescope into space. It's about the size of a bus. But we then upgraded it a couple times. And so it then got an infrared camera in 2010. And that allows us to look very, very far back. And so it's that infrared camera that allowed us to look for those pictures for this galaxy that we found with the ground-based telescope. And so this is allowing us to look further and further back. And so that's kind of the idea. Is we want to study more and more of the early universe, but we need to be able to see that far back in time. So we need bigger, better, more advanced, and infrared telescopes. So Hubble launched in 1990. It orbits the Earth. And like you saw before, its mirror was 2.4 meters. The whole thing is roughly the size of a bus, like that whole telescope is. And I assume a lot of people are familiar with the Hubble Space Telescope. It's responsible for most of those pretty pictures. It's been incredibly inspirational. And over the 30 years that it's been in operation, I think it's genuinely changed our view of the cosmos. We've learned more from this telescope than we expected. And also we've done some really cool things with it. And it is responsible right now for the most distant galaxy that we've found. So the current record holder is now GN-Z11. GN because it's in a field called Goods North, which also is an acronym, and then Z11 because it's at Redshift 11. And so what I'm showing here is, again, another schematic of the history of the universe, where on the left is the present day and on the right is the Big Bang. We could be consistent in the way we show these things, but we're not. So what you're looking at here is the previous record holder, which is about the redshift of redshift 8.5, right? And then this galaxy is now at redshift 11, meaning it is now like 300 million years sooner than the galaxy we studied before. And so learning about these galaxies, even detecting them right now, is incredibly complicated. And then again, there's a picture from Hubble. In the background is the whole field that Hubble looked at, and then a zoom in of this galaxy. Again, it's going to be red because that is the wavelength of light that it's stretched to. And you can make simulated images of these galaxies. And I believe there is a link to both of these, to news articles about both of these galaxies that have more information about how they were discovered and these kinds of things. So we're pushing further and further back and looking at galaxies earlier and earlier. And so right now we're kind of in the process of even just being able to find them. We're breaking these records because it's incredibly difficult to find these galaxies. And what do we want to do with them? Like, okay, we found it. But now we want to study them, but we also want to look at things that are further away. So we're going to kind of try to do both. So this is the James Webb Space Telescope. And if anybody has watched our show, I have to drink every time this thing is mentioned. But it is also 1 p.m. So we're going to just stick with coffee for a second. We'll save the rest of that for the trivia afterwards. But the James Webb Space Telescope is scheduled to launch in October of 2021. It's been scheduled many times, but we're hopeful. And it's not going to orbit the Earth. It's actually going to go to L2, which is 1 million miles past the moon. And so while we could upgrade Hubble, we can go up there and we could fix it, because when it launched, it actually had a problem. We won't be able to fix this one. And so it's going to have to launch. It's going to travel 1 million miles past the moon, and it's going to have this big heat shield to block the heat from the Earth, the heat from the sun, and the heat from the moon from the telescope, because infrared is heat wavelengths of light. And we're going to look for galaxies early on in the universe. We're going to be doing some incredibly amazing other science, planetary science, looking at atmospheres of planets around other stars. This telescope can do all kinds of things. We don't just use telescopes for galaxies, although I am slightly biased, and that's all I use them for. This telescope is 18 mirror segments, like you saw in that picture. It's much bigger than the Hubble mirror, and it's gold plated, not just because it's shiny and not just because it's gorgeous, but it's because gold actually reflects infrared wavelengths of light. And this telescope is meant to operate in the infrared, but we needed to have a resolution the same as Hubble. So we needed an infrared telescope with the same resolution as Hubble has in the visible, which means we need it to be bigger. So this telescope is roughly the size of a tennis court, hence like the whole thing, not just the mirror. The whole thing is about the size of a tennis court, hence the tennis court in that previous schematic. So I don't know if you're familiar with the Hubble deep field, which is this image here on the left. So Hubble decided, well, Hubble didn't decide, it's a telescope. The people decided, that what we wanted to try to do with some discretionary time we had, the director of the institute that runs Hubble has time where they can decide to apply to certain programs. There was a proposal to stare at a spot in the sky that looked empty and to see what we could find. And so we stared at this spot in the sky for a long time. And you can see here on the bottom right, this is the size of the spot that we're staring at compared to what the moon looks like. If you were to look up, and this is how big the moon looks to you, this is how small this little spot of space is that we stared at for many, many hours with the Hubble Space Telescope. And in this image are thousands of galaxies. Every single spot in that image is a galaxy, with the exception of a few things that have like the little crosshatches. Those are stars in our own galaxy that are kind of in the way. And so all of these little dots are galaxies. And in fact, some of these most distant galaxies that we're finding are in these images. And we wouldn't have known that billions of galaxies existed if we hadn't decided to stare at what we thought was nothing for a long time. And so sometimes things like that surprise you. We learned so much about how big the universe really is from the Hubble Space Telescope, and it's done some incredible science, and it's still going. We are supposed to be proposing to use it in a month or so. So we'll deal with that later. So what would it look like if we had the James Webb Space Telescope and we did a similar thing? So this operates in visible, ultraviolet, visible, and a tiny bit of infrared. And so these are all the wavelengths that you're seeing here in this image. So we've simulated what it would look like if we did the same thing with the James Webb Space Telescope when it launches. And there are more galaxies in this picture. There are even more things that we can study. There are different types of galaxies. There are different colors, there are different sizes, there are different shapes. And there's galaxies that are further away because it's looking at wavelengths that are stretched longer. So light that's been left earlier than the ones that we can study with Hubble. And so this telescope is going to open up all kinds of science. And also, again, it's going to be incredibly inspiring and put more context to our place here in the universe. That's great. Those are very tiny spots in the sky. And I am super excited for Jwst, which I haven't been drinking, so I'll have to catch up. But that's not the only thing that we have planned for the future, because those are tiny little spots on the sky. That little square is one camera field of view for Hubble, and it's the same for Jwst. They're the same about size that you can look at. And so if you want to look at a bigger area of space, you have to take a bunch of pictures and put them all together. And that takes time and that's expensive. And if you want to look at something for many, many hours, you have to do many, many hours at every single location you want to look. And so the Roman Space Telescope, aptly named for Nancy Grace Roman, used to be called the W1 Telescope, but I'm glad that they renamed it. It is a telescope that's going to be launching mid-2020s, and its field of view, one image that this telescope can take at a time, will be the same resolution as Hubble, will be infrared wavelengths like Jwst, is going to be 100 times that of one image of Hubble or Jwst. So that little square there in the middle is what one picture with either Hubble or Jwst is going to be. And the Roman telescope can take one picture that's the size of this blue square. And so not only are we going to be able to study a bunch of things in their universe, but we're going to be able to, again, put things into context. Right now, we're trying to break records because we only know about 5 or so galaxies, 10 galaxies that existed in the first billion years of the universe's history. And now we're going to be able to study galaxies in a bigger, broader context. And so with the future of telescopes, it's very exciting because we're going to be able to do this and put, again, not just find them, but study them and put them into different categories of types of galaxies. And I would be remiss if I don't mention a thing that the University of Texas at Austin is involved in, and that's the giant Magellan telescope. So right here on the bottom is a artist rendition because it is currently being built. And so the structure is being built in the Atacama Desert in Chile. And it has those big giant mirrors that were in that schematic before. And like I said, like we're looking at small spots of the sky with Jwst. So on the left is kind of a simulation of what the density of the universe would look like. And so in this image, from left to right is increasing time, and then top to bottom is space. And so if we're looking at just Jwst, we're only seeing a little tiny spot. And with the Roman telescope, we'll be able to see 100 times that. But it's, again, hard to get telescopes into space. And so we're building big telescopes here on Earth that are able to collect a lot more light. And this one will have lasers And so we can actually deal with removing some of the atmosphere. If you shoot a laser up into the sky and you can kind of measure what happens to that light by the atmosphere, you can start to subtract that out of your data. And so there's really cool things and technological advances that we're getting built so that we can kind of do this from the ground, because we need really big telescopes for this. And so that big circle right there, that's going to be how much we can look at with one image from the Giant Magellan Telescope. So all of these things are super exciting and they're all coming up. But right now we're still doing really cool science. And so stay tuned for the next big discovery and the next big break. I can talk a little bit specifically about things I've found, but I just thought I'd give you an overview of kind of how we do this type of science and what it means. And I will leave you with this video of the James Webb Space Telescope. Like I said, has to launch into space, travel 1 million miles past the moon. But what I didn't tell you is it's a giant space transformer. It is going to open itself. It's a tennis court. You can't fit a tennis court into a rocket. So you gotta fold it back up, stick it in a rocket, and then it's gonna have to unfold itself as it travels 1 million miles past the moon. And all of these moving parts and all of these things is an incredible feat of engineering. And like we mentioned before, like it is hard to do these things. And so there have been many tests and many checks and there's been delays, but it's gonna work. It's gonna work. And so we need to make sure that it's ready to go and everything is prepared and everything is going to work, because Hubble was close to Earth. We could go fix it. JWST is gonna be way too far away for us to go fix it. And it's gonna have to do this all on its own. So I'll just leave this video playing for you guys to watch this giant space transformer telescope. That will definitely work. Thanks.
Perfect. Thank you very much for this amazing talk. I really enjoyed it. And I know how hard it is to explain how Redshift work, and I think it's a very good explanation.
Thanks. Yeah, it's a term that just we could have done better.
To put your head around it, but I think you've done a very good job, because we have like about a gazillion questions.
Oh crap! Okay.
So let's get into it. So from YouTube, from Roger, we have the question: quite an advanced question, I have to say. What did the early superclusters look like 13 billion years ago?
The early superclusters.
Yeah.
Oh, okay. Well, I think Jackie's probably here, so she might be able to speak to that. That's what she studies. I don't think right now we have a super good observational understanding of this, because again, what I'm looking for is ultraviolet radiation from these galaxies, and our field of view for the telescope that we're using is very small. And so clusters are typically large clusters of things. Now, when they're closer to us, we can fit them all in one Hubble image. But when they're further away, things are much more distant. And so we need a bigger field of view. And we can do these kinds of things with ALMA. So radio observations are typically how we're looking for superclusters. And Jackie's definitely the expert here if she's in the chat, I hope. But she can talk about how far away or how distant things are that might be gravitationally bound or starting to cluster and clump. There was some overdense areas of the universe early on, and that's where we think clusters of galaxies started to form. And that's actually kind of where I'm looking for these, for the galaxies that I'm looking for. And we don't know exactly how big they are by observations, but we have simulations that can kind of tell us how big these things would be. I can't give you a number off the top of my head, Roger, but hopefully Jack is around to help.
If she is, please help us answer this question. But so you're looking at the densest region then. You're trying to look at the densest region because that's the most likely you will find galaxies. The early galaxies.
Well, yes, because that's where more galaxies are. But also, I skipped over some parts about reionization, and so I can stop this crazy video just for a minute and kind of show you what I'm talking about here. So we're looking at this epoch of reionization. So this kind of middle portion where you see kind of all these bubbles with galaxies inside of them, and so these bubbles are where the dense parts of the universe are. And so this is where more galaxies would have been. This is where they would have been emitting more radiation and more light. They would have more bright young galaxies and bright young stars that are emitting like UV radiation. There's supernovas going off because they're very chaotic and they're forming and all these stars really, really fast. And so these are the very, very bright things. These are where the big bright things are going to be, because that's where big, like you need to kind of have a bunch of galaxies fall in and merge to make a big galaxy. And so in order for us to see something, it needs to be quite big if it's very far away, because it's going to be faint. And so all of these denser areas are where we would look for galaxies, or where we're going to even see them right now, right? It's not that we're necessarily like, I'm going to go look at this dense region. We're like, oh, I see this thing, so it must be a dense region, because it must be big enough to be able to see right now with our current technological capabilities. And so it's kind of a, you know, a bias that we have, but it's also recognizing that this is what we're capable of detecting right now.
Okay. Super cool. And another question by Roger: how large was the universe 13 billion years ago?
Not as big as it is now. I don't know how big the universe was then. I mean, ultimately, the observable universe is a finite size, but the universe itself is infinite. And so I'm going to go with infinite because it's not the wrong answer.
Yeah, pretty safe answer here. Then we have more questions from YouTube. From Taylor, we have: how long is the total exposure time for the Hubble Ultra Deep Field?
Oh geez, it's been looked at many times. And so like total exposure time that we have, I don't know what the hours is. I want to say it's like 10,000 or something, but that might be an overestimate. We typically don't think in terms of exposure time, and in astronomy we think in terms of how deep the image goes, meaning how faint of an object can we detect in this image. So which means you have to stare at something for a long time to detect an object that's this faint. You have to stare at it for this much time. Now, if it's this faint, you have to have this much time. And so we typically think in images of like depths instead of necessarily exposure time. So I would have to look up the actual number of hours because I normally think of it in depth.
Okay. Yeah, we have so many questions. Assuming that we have an infinitely advanced telescope, what should we expect to observe?
Everything, all of the things. Again, I'm very, very biased because the things that I study are galaxies in the early universe. And what I always want to look at are galaxies in the early universe. And that's not to say that this is the only important discoveries to be made in science, in astronomy. There's a lot of really cool things that can be done. If we wanted to put a giant radio array on the moon, we could do amazing things with that. We could study these protoclusters. We could look at, you know, planets that are being formed around stars nearby. You can watch them being made in the little dust clouds around stars that are being formed right now from the ground with radio telescopes. If you were to have a bigger one, you'd have even better resolution for things like that. If you had infinitely powerful telescope, I would look at everything. You know, you could take images of black holes. We needed a telescope the size of the Earth in order to take a picture of a black hole, but we did it. And so if you had a telescope that could do anything, do everything.
Yeah. That. Okay. Sounds very good. Okay. Is there a unique identifier of the first stars that would allow you to identify them? Or are there too few identifiers? Or are they too short-lived to find them? So I'm guessing as identifier would be like a spectral line or some properties that would tell you this is the first.
Yeah, so the first stars are gonna form out of the things that existed when they were made. And so the Big Bang made hydrogen and helium, trace amounts of lithium for Danny. But all they had to make stars out of were hydrogen and helium. And so right now, stars are made out of all kinds of stuff. We've exploded supernovae that have made all kinds of elements, and then all the explosions make even more elements. And there's a really cool like periodic table which shows you like where all the elements came from in space.
Yeah.
Like what made them, if it was a neutron star merger, or if it was, you know, a supernova going off, or if it was, you know, being fused in the core of a star or something like that. There's really cool like thing that shows you all of that. But the first stars only had hydrogen and helium. And so all they're going to have is hydrogen and helium, but they're also going to be big, they're going to be short-lived, and it's going to be very difficult to find them. And we hoped that we would be able to do this with JWST, with the technological capability that we have for it. But we aren't maybe going to be able to do that to the degree that we hoped so. But these galaxies are going to have different spectral signatures. They're going to have different like components to them. It's just going to be hydrogen and helium, whereas stars now have all kinds of stuff. And the sun has, you know, all kinds of different elements that you can see if you take a spectrum of it. And so we have people who do like simulations of like, if we had a star that just has this, what would it look like if we observed it? And then that's how we kind of go. We have models to fill in the gaps for things that we haven't been able to observe. And then we observe things, and then we update the models, and then the models tell us what we think we should observe. And then we go back and forth. And so we need to fill in some of the gaps because we don't control this massive experiment of astronomy. Our lab is space, and it doesn't care what you're looking for. And so you kind of just have to go and look and see what you find and compare to what you expect and what we understand of physics. And so I think to answer your question, they would look different because they would emit light differently because they're made of different things.
Okay, but we've theorized all of that, and we kind of trying to look for it.
We have an expectation for what it would look like. So if we see something that looks like that, then we can be like, oh, I think that's what that is.
Yeah, really cool. Another question from YouTube. What's the highest redshift galaxy you'd expect to see with JWST?
Oh, I'm really hoping for like 13. But if we have gravitational lensing, it might be higher.
Mm-hmm.
But that's going to not be in like large enough. Again, we are going to try to break the record continuously.
Yeah.
This is a thing that we're going to keep trying to do because not only is it fun, but it's also interesting. It's interesting to find galaxies and see how they differ. Like, how does this galaxy that exists at redshift 11 differ from the one that exists at redshift 8? Mm-hmm. We don't know a whole lot because right now we're barely even detecting them. All we're seeing is like the hydrogen in them, but we're not being able to characterize them. So I have a collaborator who's looking for carbon emission from galaxies early on, so we can say something about the properties and the physical things that are going on. So shout out to Taylor if she's here. She's got some cool talks about what she's doing, trying to even understand and classify the galaxies that we're trying to detect. And so, you know, the most distant galaxy that I would hope to find would be something, you know, around redshift 13 or, you know, like 400, 300 million years after the Big Bang. But ultimately, I just want to find more of them. So we'll be able to find more galaxies that are at redshift 9 or 10, which is incredibly difficult to do now. Well, hopefully I've put in a proposal to use the telescope to do this kind of science, and hoping to find something, you know, on the order of like 20 to 50 would be game changer, because we know about, you know, 5 right now. And so that would be, you know, really exciting to do. And that would be just some of the first things that we can do with the telescope. If we have the telescope for years, we would be able to do things like the deep field, and we'd be able to see more distant things because we'd have more exposure time and more depth to our images.
Yeah, the main point being that this telescope is going to be a game changer.
Oh, so in so many ways, and not just for galaxies. Like, I don't want to, you know, ignore all of like the exoplanet people and all the other things that it can do. But yeah.
Okay, we're gonna go with a few more questions and then move on to the pub. So if I didn't have the time to ask your question, guys, please join us later on. If we assume now that the light emitted by a planet's star gives us information about it in the past, but if light changes over time, as you explained at the beginning, how can we know about that object at all? Like, how can we reconstruct, you know, if the lane changed on the way and got eaten up, as you said?
You mean, how do we know what it looks like now? Like we see the light that left it as it existed, however long, like four light years away.
But no, right? Exactly. But you said that we see the light, but the light has been changing on the way. It has been like to higher wavelengths. And so how can we? I'm guessing the question is, how can we know about that object if the light has been changing so much on the way?
Yeah, so again, this kind of goes back to how we have models. So we're like, here's what we expect this thing to look like. We expect there to be hydrogen here, and we expect there to be carbon here, and we expect there to be oxygen here, and then we see the same pattern shifted, right?
Mm-hmm.
So we see this same pattern but shifted to a longer wavelength, and then I can be like, oh, I see this pattern. That's hydrogen. That's helium. That's oxygen or carbon. And then we'll be like, okay, so the amount that it shifted tells us how far away it is. And then, like how much oxygen or how much carbon or how much hydrogen is in it tells us something about what's going on physically in that object, because we can simulate that based on the physics of what we understand is going on in the galaxy or the star or whatever it is that you're looking at. And so we can say something about it because of the physical processes that had to exist to create those signatures. To have that much oxygen, you need to have this many stars that have formed and have emitted this much radiation, and have this much carbon. You needed to have this kind of interaction and those kinds of things. So you're looking at light, but then you're telling yourself a whole lot about physics because of how quantum mechanics work and how we see those elements exist because of certain processes that happen.
Okay, so it's the emission lines that allows us to reconstruct. Okay.
I mean, there's also absorption line. There might be something in between. There's a lot of components that go into it, and it's a complicated process, and it is not easy. And so you need to account for not only are you the thing you're looking at, but like often there's stuff in between you and that object. It's not like it just traveled all through the universe for 13 billion years and didn't hit anything else but your telescope. I mean, that is quite serendipitous, but so there you'll see absorption as it travels through different things. And so you can kind of also say something about the universe that existed at different times this is how we look at quasars, and understand kind of like the composition of the universe at different times is like how much light was blocked as it traveled
on the way to us.
Yeah.
Okay, so as the last question before we move on, I think it's a fun one. Can you give a percentage of how likely you think JWST will launch this year? And is there a betting pool for all the things that could go wrong with it?
Why would you ask that? I don't want to bet on it. It was going to launch in October of 2018, and I had my whole PhD planned. And it is 2021, and it is going to launch in October. And I've done something else with my PhD, and so I hope that it launches. I mean, I genuinely want it to launch as soon as possible because I want to use it, and I'm very excited for it. And again, like we said, it's going to be a game changer and do all kinds of amazing things. And we have. I'm lucky to be on teams that already have scheduled time on the telescope. And so I'm excited to get to use it. But I don't want it to launch unless it's ready, because there is no point in launching it just to launch it. It needs to work. And so I'm torn. I'm of two minds here, because like I want it to go, but I need it to work. And so if it needs to be delayed to work, then I would rather that be the case than not.
So how just personal opinion, like just like this, how likely do you think? Or do you don't want to jinx it, so you don't want to say?
I don't want to jinx it.
Okay.
I would say I'm more optimistic now than I have been.
Okay. Very good. Very good. Thank you very much for this amazing talk and Q&A session.
Thank you for having me. This is fun.
Are you going to participate to the amazing quiz after? Although you made some of the questions, you can still try.
I guess I can't answer them, but yes, I will go.
Perfect. Then we'll see you later in the ZooPub. Bye.
Thank you.
And now Jake is gonna take over to tell you guys where you should go to participate to the amazing pub quiz. Bye.
Thanks, Laurent. I was just also thinking to say to Rebecca that you could tell us your percentage once you're in the Zoom pub, because then you're not recorded on YouTube for all history about your percentage guess about the chances of launching. So go to the pub and tell us there in secret.
Okay.
We hope you all come and join us in the Zoom pub. That's http://stem.000/Zoom pub. And we will be there for the quiz in a couple of minutes. I'll switch over there. So please follow that link now and head over for the quiz, and also time to hang out with the organizer of Astronomy on Tap Groningen. Also, our speaker Rebecca will be there, and we will have continuing a great time. So head over there now. We'll leave this up for about another minute so you can see the link. Otherwise, just rewind the stream a bit and look at it. I'm sorry there's not 2 slashes at the beginning. Every single time I forget to change it until I see it here. I know I was talking to everyone in the world, but maybe you can remember before next time that I need to change the URL in this slide. But I think everyone in the universe knows that it's ://. So please head over and join us there now.